by the specific volume is equal to at the inlet is equal to outlet. A3 velocity at the exit section of a pipe 3 divided by the specific volume V3. A4 into A4 is nothing but this is the area of the pipe 4. So A4 and velocity of the flow at this section, that is V4 divided by the specific volume of the fluid at the fourth exit section of a pipe. So these things are there, and now you have to write the energy balance equation for this. So the mass balance equation and also the energy balance equation, which you can put it in the same fashion, right? Next one is this is the energy balance. So that is at the inlet section m1 dot into m1 dot, because always this is in kg per second or it is kg per hour, kg per second or it is kg per hour, and this is in kilojoule per kg or joule per kg. If it is kilojoule per kg, then you will get as 2000, and here also 1000 in kilojoules. So that you should not forget. And here also this H2 is in kilojoule per kg, and this is also kilojoule per kg, and this is also kilojoule per kg, and d bar q by dt. So these are all the inlet sections is equal to the exit section m3 dot into h3. And now here the left hand side, whatever the notations or whatever the unit compatibility is there, so to the right side also the same units you should have to mention. So if this H3 is in kilojoule per kg, then here V3 by 2000, Z3 by 1000 plus M4, H4 which is in kilojoule per kg. This is also kilojoule per kg. This is also kilojoule per kg plus d bar w by dt. So this is how the steady flow energy equation representation. Steady flow energy equation representation. So once after getting this particular derivation, right, for multiple stream fluids, then now the time has come to solve the that is applying the steady flow energy equation for solving the numerical problems. For solving the numerical problems, so there are certain applications are there in your syllabus. The nozzle and diffuser. So nozzle is nothing but the here this is the nozzle. This is the nozzle. So steady flow process involving one fluid stream at the inlet and exit section of the control volume. So both are the same. That is, you can get the same. That is here what question which you can expect. Deduce the steady flow energy equation applied to the nozzle, throttling valve, compressor, turbine, heat exchanger. So this type of question you can expect. Deduce the steady flow. That means what is the steady flow energy equation? So when you write the steady flow energy equation here, when you write the steady flow energy equation, that is here m1 dot into h1 plus c1 square by 2 plus gz1 plus heat flow rate is equal to m2 dot into h2 plus c2 square by 2 plus gz2 plus work flow rate, that is W, right? So this is the expression. Now here the nozzle is nothing but it is used this setup the nozzle. So this is nothing but the convergent nozzle, and this is used to increase the kinetic energy of the flowing fluid. This is used to increase the kinetic energy of the flowing fluid. Whereas the diffuser, so this is the diffuser. This is the nozzle. This is the nozzle. Diffuser, it increases the pressure energy of the fluid. So here the pressure energy of the fluid is going to increase, and here the kinetic energy of the flowing fluid is going to increase. Kinetic energy of the flowing fluid is going to increase. So when you apply the steady flow energy equation, here when you apply the steady flow energy equation, so the according to the continuity equation, what is that? M1 dot is nothing but equal to M2 dot. So that is nothing but equal to A1 C1 divided by the specific volume is equal to A2 C2 the specific volume. So this is the continuity equation, and you should not forget about this continuity equation. With this section where you could be able to find out either A1 or you could be able to find out A2 by giving the by uh, getting the input data C1, C2, specific volume V1, specific volume V2. So out of these four variables, three will be known and one will be the unknown. That one unknown value you should have to find out. That unknown value you should have to find out. Now, when you apply the steady flow energy equation to this one, so here this is completely the insulated. See here, this is completely the insulated part. That means no heat transfer, no heat exchange. It is completely insulated. So that means here the heat transfer is 0. And with this setup, no work transfer. So here the work transfer is also 0. The heat transfer is also 0. Potential energy, that is also 0. Potential energy, that is also 0. So finally, what is the expression that you are going to get? You will get as H1 plus C1 square by 2 is equal to H2 plus C2 square by 2. H2 plus C2 square by 2. So that is H1 is equal to, you can get it as H2 plus, when the inlet kinetic energy is 0. Why? Because the nozzle is nothing but it is used to increase the kinetic energy of the flowing fluid. So at the exit section, you can find out the kinetic energy, but at the inlet section, the kinetic energy is negligible. So that's why it is 0. So you can find that at the exit section, that is C2 square by 2. C2 square by 2. So finally, you could be able to find out the exit velocity from the nozzle. Exit velocity from the nozzle. So that is nothing but equal to 2 into H1 minus H2. 2 into H1 minus H2. So this is in meters per second. And where H1 and H2 is in joule per kg. Where H1 and H2 is joule per kg. Right? So this is how you can, that means here applying that is now what you are going to do is, so here using the steady flow energy equation, this is the steady flow energy equation, and deduce, so from that particular steady flow, then you have to build up, so what is the velocity of the exit, velocity at the exit section of a nozzle, velocity at the exit section of a nozzle, right? So this is how the things are going to be getting. So that is deducing the steady flow energy equation. So the same concept you can apply it for the diffuser section. So in the diffuser section, it is going to increase the potential energy of the flowing fluid. Sorry, the pressure energy of the flowing fluid. It is going to increase the pressure energy of the flowing fluid. Next one is there are some other applications are also there. So far just now covered the nozzle and diffuser part, nozzle and diffuser part, and the remaining things, that is the compressor and turbine is there. So we will apply the compressor and turbine section, right? So go through the Pekenak textbook, and very good things have been given there, or try to follow this particular lecture. So the compressor, so right, so the compressor is nothing but the flow rate entering, that is low pressure fluid low pressure fluid will be entering at this section, and a high pressure fluid is going to leave. High pressure fluid is going to leave. That is the high pressure fluid outlet. So what is the importance of a compressor? Compressor is nothing but it is going to increase the uh, pressure at the outlet side. High pressure, right? Pressure at the outlet side. So the compressor, if you observe the reciprocating, there are when you talk about the compressor, there is various varieties of compressors are there. That is, the reciprocating compressor is there, rotary compressor, axial compressor, centrifugal compressor. But whatever it may be the compressor, you need to apply the steady flow energy equation. You need to apply the steady flow energy equation, right? So in the same way, that is this is the compressor. Here observe the inlet part and outlet part. If it is a turbine, then here this is the inlet point, right? So the mass flow rate of the fluid, which is in kg per second. Some flow rate of a fluid is entering at the inlet section of a turbine, and it is going to leave at the exit section. So this is the section 2 that is, this is nothing but the mass flow rate m2, right? And this turbine is gets insulated. If this gets insulated, then q, heat transfer, is nothing but equal to 0. So from the turbine, and when I talk about the turbine, the turbines, there will be the different things are there. What is that one? There, whether that particular turbine is a gas turbine or it is a hydraulic turbine, right? Hydraulic turbine, or it is a nuclear turbine, or it is a nuclear turbine, that is in nuclear power plants. So nuclear turbine, hydraulic turbine means hydropower plant, gas turbine means gas turbine power plant, and the another one is a steam turbine. Another one is steam turbine. So the turbine, whatever it may be the turbine, but there are different varieties. Gas turbine is there, hydraulic turbine, nuclear turbine, steam turbine is there. And what is the functioning of this turbine? Turbine is going to produce the net work output. So the turbine is going to give the work output, right? The turbine is going to give the work output. So that is W is positive. Whereas for the compressor, you have to give the work input. For the compressor, the work input is there. So that is, this is the work input, right? So here W is nothing but minus sign. Here W is nothing but positive sign. Here W is nothing but positive. And even in the compressor, there are the, the reciprocating compressor, and another one is the rotary compressor, and you can different varieties, just I am discussing, that is axial compressor, which is used in gas turbine application, aviation purposes. Axial compressor, and the another one is a centrifugal compressor, centrifugal compressor. So whatever it may be the compressor or whatever it may be the turbine, when you are applying, what is the steady flow energy equation? That is H1 plus C1 square by 2, right? C1 square by 2 plus GZ1, this is all closed, right? Plus D bar Q by dt is equal to H2 plus C2 square by 2 plus GZ2 by GZ2 plus D bar W by T, D bar W by dt. That means here for a turbine, it is a positive, right? So for a compressor, it is minus. This is what the student has to observe. But anyhow, this turbine is insulated one. So this particular turbine is insulated one. Then in this case, kinetic energy terms are neglected. Kinetic energy term, right? And this heat transfer is also 0.